Hello, everybody. Welcome to the Atto Fridays. This is the first one of 2025. And it's a pleasure to have today Professor Maria Chekhova from the Max-Planck Institute for the Science of Light in Erlangen, Germany. She obtained her PhD at the Lomonosov University in Moscow, Russia in 1989. And she worked there until 2009 as a researcher and a group leader. And meanwhile, she was also a visiting professor at the University of Maryland and in the Metrology Institute in Turin. And in 2007, 2009, she was a Mercator Fellow of the Universität Erlangen-Nuremberg. And since 2009, she leads an independent research group at the Max-Planck Institute for the Science of Light in Erlangen, Germany. And since 2020, she also holds a professor position at Universität Erlangen-Nuremberg, and she's a visiting professor at Technion University, Israel. And her research area is generation application of non-classical light, with a very special focus on extreme cases, bright cases of light manifesting quantum behavior on the one hand, and nanoscale sources of quantum light on the other hand. She has authored over 200 papers and a book, and she's a fellow of Optica and a deputy editor of Optics Express. So we are really pleased to have her here now. Welcome. You are a pioneer in this type of work. And she'll talk about bright squeezed vacuum and its applications in strong field physics. So the floor is yours. Feel free to take it, and welcome to the Atto Fridays.
Thank you. Thank you very much for the introduction, and thank you for the invitation. So just to explain where I am, this is Europe here, and the city of Erlangen is not very large. You see, it's somewhere to the north of Munich, about 200 kilometers from Munich. And then in this very nice small city, there is an institute. That's where I am, the Institute for the Science of Light, Max-Planck Institute for the Science of Light. And here I have my rather small quantum radiation group. This is the outline of what I'm going to talk. I'm going to introduce you to the, I think, exciting subject of bright squeezed vacuum. And then I will show what we can do with this bright squeezed vacuum. We can enhance multiphoton effect and observe things like heavy tail distributions, extreme events, also called rogue wave behavior. And then I can show how this bright squeezed vacuum can drive electrons out of needle tips. And finally, how this bright squeezed vacuum can drive high harmonic generation. So this is my plan, and then give some conclusions. And by the way, I will not talk of attoseconds, but our pulses are rather of atto-minute duration, if that's okay. But if you invited me to this Atto Friday event, then you have to suffer from the absence of attoseconds. Okay, so what is bright squeezed vacuum? The effect that we use is called spontaneous parametric down conversion, and it occurs in nonlinear crystals, crystals with second-order nonlinear susceptibility, like crystals that generate second harmonics, probably everybody knows. But unlike second harmonic generation, in our effect, one photon splits in two. In the second harmonic case, it's the other way around, two photons merge into one. But in spontaneous parametric down conversion, let me show it once again, one photon that we call pump photon splits in two photons. So a photon pair is appearing, both photons at the same time. But we are interested in the regime where we send a lot of pump photons, really bright beams or strong pulses, and then there are many, many pairs. So these are many, many pairs. And it so happens that photon pairs generated at the beginning of this nonlinear crystal, if the nonlinear crystal is thick enough or the pump is strong enough, then this pair generates, stimulates the emission of next pairs and then generate next pairs. And along the crystal, the number of pairs grows exponentially. So it's not just few pairs of photons, but these are strong beams at the output of the crystal, really bright light. That's why we call it bright, and why it's called squeezed vacuum I will explain in a bit later. So this is how it works. Exponential amplification of light along the crystal, but also exponential with increasing the power of this pump laser. So there is these photons are provided by a laser, produced by a laser, and as we increase the power of this laser and look at the output of the signal, we see that it increases exponentially. And if you are interested in the number of photons per mode or even per pulse, it will scale as sinc square. This is hyperbolic sine squared function of the value we call gain. And this gain, this G, can be as high as 5, 10, maybe 15. So this number is then very, very high, and that's why we call it bright. The parametric gain G scales with the second order susceptibility of the crystal that I introduced, the pump the pump field amplitude and the length of the crystal. And this is how it looks if we pump really strongly the nonlinear crystal. Here is a paper screen, and on this paper screen we see the radiation emitted by the crystal, and it has these colored rings, which probably people heard about, people who are interested in spontaneous parametric down conversion. Such bright rings are typical, like the signature of this process. But in our case, they are so bright that you see the reflection in the optical table of these rings, and the mean number of photons can be as high as 10 to the 13, which makes it similar to in brightness to lasers. And we were not the first to observe this effect, I must say, but we were the first probably who found it very interesting. Because when the spontaneous parametric down conversion was first discovered, and it was in 1967, interestingly, 3 works appeared simultaneously. 2 works were published in the same issue of Physical Review Letters in 1967, and 1 paper was published in the Russian Soviet journal Jet Letters, and then there was the theory paper by David Klishko, also in Jet Letters, in the same issue. And all these experimental papers, in fact, used the strong regime of generation of photon pairs. There were many photon pairs because they all used pulsed lasers. And for instance, in this second paper, when they plotted the output power versus the input power, which was here in megawatts, peak power, of course, they still had linear dependence, but I think it was because they just probably didn't have very efficient crystal, because in this pulse regime, they would definitely see exponential behavior in a more efficient crystal. I think they used the ADP. And then in this second or third paper, they saw rings, typical rings, and probably colored, but they took a photograph, a black and white photograph, of course, at that time, and they didn't look at the dependence of the output radiation on the input radiation, so they probably overlooked this exponential behavior. But already in this theoretical paper, it is mentioned that when the parametric gain is very high, then the connection between, well, this is input and output, it is nonlinear, and it makes possible to determine this gain by looking at this exponential development of the signal. So this was known for a long time, but no one was really interested in this, as we call it, high gain regime of parametric down conversion. The interest came in the 1990s, when people started to think about a Schrödinger cat. Whether this Schrödinger cat, well, let me remind the situation with the Schrödinger cat. It was a Gedanken experiment by Erwin Schrödinger, that a cat is entangled, so quantum related to the decay of a particle, and if the particle decayed, then the cat should be dead because some hammer breaks the bottle with some poison and the cat is dead. So because the quantum particle is in a superposition of state before decay and after decay, then the cat is in a quantum superposition of dead and alive. And obviously, we never see such cats who are in a superposition of states. They are always either dead, unfortunately, or better alive. But the question was, how large a quantum state like that can be? Can there be a macroscopic state of matter or light that shows quantum behavior? And Francesco De Martini, I think, was the one who was really interested in this high-gain optical parametric amplifier. This is optical parametric amplifier, so the same crystal basically as we use. And can we amplify a single photon so that it becomes a macroscopic state, a macroscopic superposition? And that's when people started to look at high-gain parametric down conversion, searching for quantum features. So what quantum features does this state of light have? There are two different regimes. First regime, where the two photons, we call them, by the way, signal and idler photons, and when there are many of them, they form these beams, bright beams, signal beam and idler beam. So in some situations, they can be of different color. For instance, one orange, the other red, or even infrared. And then because they are always emitted in pairs, these photons, then if we look at the numbers of photons emitted in two modes and look at the variance of their difference, this variance is identically zero because there is always the same number of signal photons and the number of idler photons. It's convenient to normalize this variance to the mean of their sum, these numbers. And then what we get is so-called noise reduction factor. So this noise reduction factor ideally is zero if there are no losses between the detector and the crystal. But even if there are losses in real life, this noise reduction factor is less than 1, and this is a quantum feature. So we say there are subshot noise correlations for two coherent, because the shot noise, the unity value is achieved if we send just two coherent beams instead of twin beams. And this effect was observed for the first time by the Italian group of Paolo Di Trapani in 2004. They just looked at this. What is plotted here is this noise reduction factor, and what is plotted, and the horizontal axis is the sum number of photons of signal and idler. And as we increase this brightness of the beam of light, we gradually not see stop losing. We lose the quantum features, but here in this area below some critical number, we still see noise reduction factor below 1, and this shows that squeezed vacuum shows quantum features. And another experiment I want to show, it was an experiment here in our institute, in my group, and we saw twin beams. We observed twin beams obtained via another effect for wave mixing in gases. I don't want to go into details, but I think this sets the record value for the number of photons per mode that still showed this subshot noises. We call it subshot noise correlations between the photon numbers. So here the shot noise level is shown, unity, and the blue points, you see that even at numbers of photons of 2,500 per mode or 20,000 photons altogether, we see below a shot noise of subshot noise correlation. So we see quantum behavior. And that, I think, was the brightest state for which we still saw quantum behavior. And then there is another case where both photons of a pair are emitted into at the same wavelength, into the same direction, we say into the same mode. And then it's impossible to observe twin beam correlations because we cannot separate signal and diagonal photons. So we have to do something on the beam as a whole. And here I need to explain how to what kind of feature we observe here, what kind of behavior we observe here. And in classical optics, we can show electric field or optical electric field as a point in the space of real part of the electric field and the imaginary part of electric field. So electric field is a complex, optical electric field is a complex variable. But in quantum optics, real part and imaginary part of the electric field for an optical field is similar to position and momentum in quantum mechanics. And these two variables do not commute. And therefore, if we try to introduce the joint probability, one of these joint probabilities, we call them quasi-probabilities, is called the Wigner function. So when we try to put a point showing the joint probability distribution, we cannot do it because they do not commute, so they cannot be measured and even defined simultaneously. Therefore, for instance, even for the vacuum state, so when the mean value of the field is 0, there is some uncertainty around this point. And the uncertainty is called the short noise uncertainty. Let's define it as delta P naught, and it's 1/2. But there is a state, and this is actually what is called squeezed vacuum, the state of light in which the uncertainty of one of the position, for instance, is less than the uncertainty of the momentum, and moreover, the uncertainty in the position is less than this vacuum uncertainty, than this short noise uncertainty. And this is called squeezed vacuum. Moreover, this is called quadrature squeezing because these P and X are also called quadratures, position momentum. As a measure of quadrature squeezing, people use 10 logarithm of the ratio of the variance of the squeezed quadrature to the variance of the vacuum quadrature. So this is uncertainty, we just take the variance, so square of the uncertainty, and divide this red variance to this blue variance. It's very hard to observe for really bright squeezed vacuum. I will show you. Now the record quadrature squeezing has been observed for other weak squeezed vacuum. So this is an experiment by Roman Schnabel group in Germany, and I think by now probably they have better squeezing, but not much better. So the record value by that time was 15 dB. It means that the noise or the variance of the quadrature for squeezed vacuum is below the vacuum noise by 15 decibel. And if we calculate what is the Wigner function in this case is very stretched, so it is stretched in this direction of X quadrature and squeezed in the direction of the momentum quadrature, but the number of photons in this case in squeezed vacuum is only 7, so it's not really bright. And for brighter states, it's very hard to measure this quadrature squeezing. Now, just to put some order into what I'm saying. So there are 3 cases. First, very weak parametric down conversion. So photons of the pump sometimes become pairs. The gain G is very small. There is no squeezing visible. And this is the regime of very low noise. Then there is intermediate regime where this gain G is about 1. Mean number of photons is between 1, 2, 7, as I showed. And then we have squeezing, quadrature squeezing. And finally, when this gain is larger than 1, 2, 3, 5, then the mean number of photons becomes much, much larger than 1, like for a laser, and then the Wigner function is really, really very squeezed, but squeezing is easily lost under some absorption losses, but this anti-squeezing remains, so the anti-squeezed quadrature remains very large, and this is what we use in some experiments. So this bright squeezed vacuum can be written like this as a state, as a superposition of Fock states, so states with given numbers of photons. And the interesting thing about this state is that it consists only of even numbers of photons, but that's clear because photons are always emitted in pairs. So there is no single photon state, 3 photon state, but only 0, 2, 4, and so on. And there are some amplitudes by these states. The probability distribution of the photon number is given by the square of this amplitude. And if we plot the envelope of this distribution, so here I plotted the real experimental result we got from, we published in this paper. And here you see that the photon numbers span from 0 to 10 to the 13, so very high photon numbers, and we cannot see the fine structure. We cannot see whether there are odd and even numbers of photons. And in fact, this structure is very easily lost due to just tiny absorption, but still the envelope shows very interesting shape. This black line is the fit, and it has a divergence at 0, and then a tail decaying exponentially. And these are, the red are experimental points. And the important thing for what I'm going to talk about is that it has very broad photon number probability distribution. So if we take a pulse of bright squeezed vacuum and compare it with a pulse of coherent light, we see very important differences. For coherent light, there is a very pronounced mean value of the electric field, which behaves like this in time. And the uncertainty of this value, so the standard deviation, if you want, is constant and not very large. For bright squeezed vacuum, the mean field always is 0, but the variance or the uncertainty oscillates with twice the period of oscillation for the coherent light. And this leads to the observable features that we could have. And then I want to show how in some experiments we learned how to make this squeezed vacuum single mode. Well, normally if you take one crystal and you generate squeezed vacuum, then it has a very large divergence and very large spectrum, very broad spectrum. And this means basically that it is multi-mode spatially and temporally. But to have a single spatial mode, we put another crystal and amplify what is emitted by the first crystal in the second crystal. And what is amplified should be within this cone, so should overlap with the pump in the second crystal. And this way, the formulas here are very primitive, but clearly if the distance between the two crystals is large enough, we get a single spatial mode. And the same principle we used to some time ago to generate squeezed vacuum that is single mode temporally. To do this, we just placed a group velocity dispersion material between the two crystals, and this stretched the pulse of bright squeezed vacuum in time, and then it was overlapping with the pump in the second crystal only partly, and this part was amplified, and this led to single mode temporally pulse. Yeah, the other way we can use is to use just a very short pump pulse. As I said, not attoseconds, but probably attominutes, about 20 femtoseconds, 10 femtoseconds. And this is just a demonstration what can be if the pulse is very short, the pump pulse is very short. You see that this video shows pulse-to-pulse spectra. And this shows that they're mostly single mode because you see mostly a single peak or a pronounced two peaks. in this case. Right, so now I'm showing how to take advantage of this state of light. And for instance, it can enhance multiphoton effects like high harmonic generation, or maybe not high, but a few, like second, third, and fourth order harmonic generation. The trick here is that this light has very strong intensity fluctuations, and in this case, the characterization is through the so-called normally ordered correlation function, Gn, which is the nth order moment of the number of photons normalized to the mean number of photons to the power n. Well, this is just normal ordering, but in the case of very high photon numbers, it's not really important. It can be omitted. So these correlation functions for bright squeezed vacuum have very high values. Here there are some examples. So G2 is 3, G3 is 15, and G4 is 100, more than 100. For comparison, for coherent light, all these correlation functions are 1. And the rate of any n-photon effect, so the effect that requires the absorption of the loss of n photons simultaneously, like n-photon absorption, ionization, polymerization, or nth harmonic generation, it scales with the mean number to the power n, but for the same reason, it also scales with the nth order correlation function. And so there is this factor that gives the enhancement. And some time ago, 2017, we observed how second harmonic was 3 times more efficient from bright squeezed vacuum than from coherent light of the same power. Third harmonic was about 15 times more efficient, and fourth harmonic not exactly 100 times, but 70 times more efficient. And then the output photon distribution is also quite unusual because, as I said, the bright squeezed vacuum photon number distribution has this broad tail, and it's even broader with a heavy tail than the distribution of thermal light. And compared to Poissonian distribution with the same mean number of photons, it's much, much broader. And then if we look at the distribution of photon numbers in the harmonic that it generated, it has also this typical behavior in the same scale as I showed here. You see the tail is decaying even slower. And this is exactly what is called a heavy tail. And what it means is that there are, remember, the mean photon number is somewhere here, but this tail covers events that are orders of magnitude like stronger than the mean number of photons. So for instance, if the mean number of photons is here, I don't know, maybe 10 to the 3, 10 to the 4, and here there are numbers of photons 10 to the 5. Here there is a trace of values of photon numbers per pulse that we get normalized to the mean number. And you see this event suddenly is 600 times stronger than the mean number of photons. Imagine sea waves, for instance. Sea waves have average height, let's say 10 meters. So what is the probability to see a 1 kilometer wave? Very low. But here it's a very high probability. That's what a heavy tail distribution means. Right. And then we saw similar behavior when bright squeezed vacuum was sent into a fiber, coupled into a fiber, and at the output of the fiber, we saw that it broadened spectrally. If we look at, this is the same spectrum, but in the logarithmic scale, and different traces are just a single pulse spectra, single shot spectra. And you see, while in the middle of this spectrum, they differ not so much in intensity, in height, but on the edge, they differ a lot. And if we take this wavelength, for instance, on the slope of the spectrum, and look at the distribution of the photon numbers, the probability distribution as a function of the number of photons, you see that it scales as 1 over n to the 1.5, and this is an example of a Pareto distribution, a distribution that scales as a power function. And this distribution is not, even the mean value of this distribution diverges. So if you try to calculate the mean value, it diverges. And if the variance diverges even more. And here you see also extreme events. So number of photons normalized to the mean number of photons sometimes reaches the value of 150. So very, very noisy behavior. And this is interesting because it has analogs, as I said, with sea waves and other effects following these extreme statistics. Then we turned to other cases of, and even not just multiphoton events, but here we enter the field that is called strong field physics. And in this experiment, we looked at the electrons that are ejected from needle tips. So this gray thing is a nano tip, very, very small metal tip, tungsten, in fact. And then we shine light on this tip, and this light can be coherent light or our bright squeezed vacuum. And here we look at the statistics of the electrons. And of course, why we did this experiment, we wanted to see how this noisy statistics and heavy-tailed distribution of squeezed vacuum is imprinted on the electrons that are ejected from the nanotip. The experiment we had was based on a microchannel plate that just amplified the electrons, and different channels of this plate served as different pixels, and then we looked at the number of electrons that was emitted at every pulse of light for two cases, as I said, coherent and bright squeezed vacuum. And now if we plot the probability distribution of electrons emitted due to coherent light effect, we always saw Poissonian distribution. Just the mean value change, the maximum moved as we increased the mean power of our light. So here the plot shows the mean number of electrons as a function of the mean energy per pulse in the incident light, and colors correspond to the colors here. So we see that as we change the power of the incident light, just the maximum moved. But it was very different if we did the same experiment with bright squeezed vacuum. So as the energy per pulse in bright squeezed vacuum increased, the mean number of electrons also increased. By the way, it was a power law in both cases, power 4. But now the distribution became, the distribution remained just decaying, with the most probable number being 0, and this tail becoming more and more longer and longer. And for instance, if you look at the blue trace, it corresponds to this point. So the mean number of electrons per pulse was like 2, less than 2, somewhere here. But there were events of seeing 60, 65 electrons and so on. So this is exactly the same example of extreme events or rogue wave behavior. And also what we can say is that the enhancement, that compared to the case of the coherent light, we saw enhancement in efficiency, like in the case of harmonic generation. And then we looked at different situations with the number of modes in the bright squeezed vacuum. When it was single mode and the distribution stayed, it is called, by the way, a gamma distribution of order 4. And when we had many modes, the peak moved, and again we could fit this distribution, assuming just the independent modes of a squeezed vacuum. And finally, our last work was when we observed high harmonic generation, so not second, third, and fourth, but higher order harmonics, and moreover, emitted in a non-perturbative way. So this is the theoretical prediction by our colleagues from Technion, where they considered generation of optical harmonics by different quantum states of light. So this red trace corresponds to coherent light, this corresponds to the Fock state, which is really hard to obtain, and then orange is thermal light, and green is our beloved squeezed vacuum. And in all cases, the harmonic spectra looks in a way similar. So there is some kind of a plateau. So these are just numbers of harmonics. And I think they considered gases. So only odd harmonics were emitted. So these are peaks corresponding to different harmonics. And usually these peaks form a plateau up to certain order and then a cutoff. So starting from certain order of harmonic, you don't see it, the effect is very weak. And they showed that for bright squeezed vacuum and slightly, well, almost the same for thermal light, this plateau is stretched, and with a given mean power of the incident light, many more harmonics can be seen. And we decided to make this experiment. Another prediction was that the cutoff was scaling differently with the intensity of the incident light. So we decided to compare the emission of harmonics under coherent light, classical, and bright squeezed vacuum quantum light. We didn't do it in gases, we did it in solids. And in a solid, the mechanism of the effect is as follows, as shown here. A single electron-hole pair is formed by light, and electron is emitted then into the conduction band and the hole in the valence band, and then under the effect of under the field of an optical wave, they start to accelerate in this band. So electron and the hole get some momentum, and then with this additional momentum, additional energy, they finally recombine, releasing a photon. And this photon, of course, has higher energy, much higher energy than the incident photons, because, first of all, it can be because of the multiple photons causing this electron-hole pair, and due to the acceleration. And then high harmonics are emitted. But we are very interested by the fact that in squeezed vacuum, the electric field has this uncertainty at any time. And this uncertainty leads to the fact that there are simultaneously electrons accelerating in opposite directions. And whether we can see this effect or not is still an open question, because this is a superposition of electron trajectories. And this superposition is usually very hard to observe. But what we did, we built a single mode source of squeezed vacuum using the same trick as I showed you before, but just a single crystal and a mirror, so that squeezed vacuum was emitted in a crystal and then reflected back and amplified in the same crystal. And this is an example. So before this double pass, the squeezed vacuum had multi-mode spatial structure. So you see these speckles, and then after double pass, it was a Gaussian. It had a Gaussian structure. The photon number distribution is shown here. By measuring this second order correlation function, we could make sure that we really had a single mode case. The temporal mode was single because the pulse of the pump was very short. It was only 45 femtoseconds. The output bright squeezed vacuum pulse was even shorter, 25 femtoseconds. And then having a single mode bright squeezed vacuum, we could focus it into our sample very tightly. The sample was lithium niobate first, a 7 micrometer sample. We compared it with coherent light, but our coherent light was at first, now we fixed this problem, but at first our coherent pulse of light had a different pulse duration, so it had a slightly different spectrum. But still we could see that squeezed vacuum was generating harmonics more efficiently than coherent light. So what is shown here is the spectrum of second, third, fourth, fifth, sixth, and seventh harmonic. Solid line shows what we had with bright squeezed vacuum, dashed line with coherent light. The spectra are narrower, but we have an advantage in the efficiency, and the advantage is shown here. The highest advantage for the fifth harmonic is only 30. If the generation was perturbative, we would have much higher advantage. We would have, for instance, for the fifth harmonic, we would have 1,000 times enhancement, but it is non-perturbative, and we will now see why. By the way, we used also we had the advantage that squeezed vacuum has a very broad distribution over the photon numbers. So we tapped a little bit of squeezed vacuum and looked at the numbers of photons in the squeezed vacuum by using a detector, measuring every pulse. And simultaneously, we measured the numbers of photons in every pulse of the harmonics. And this is an example, so simultaneous measurement of the number of photons in a harmonic and in squeezed vacuum. And without changing the mean power of squeezed vacuum, we could see how the number of photons in the harmonic scales. And this was very convenient. So this shows, again, the same trick in comparison with what we have with coherent light. So when we have coherent light, then the left panel, the distribution of photons in coherent light is very narrow, is Poissonian. And so with a fixed mean number of photons with coherent light, we have this very small range of photon numbers, and the photon numbers in harmonic also occupy a very, very narrow range. And then to see the scaling of the number of photons in a harmonic compared versus the number of photons in the pump, we have to change the mean number of photons in the coherent pulse. And so we have a different distribution now. With squeezed vacuum, as I said, even with a fixed mean number of photons, we span the whole distribution and we see the scaling all at once. So this was already a very convenient thing. And here is a comparison. First, we looked at harmonics 4 and 5 in lithium niobate using classical radiation, coherent radiation, and bright squeezed vacuum. And we see several features. So first of all, why we see fourth harmonic? Because lithium niobate is non-centrosymmetric, it's not like a gas, and we see odd harmonics as well. Second, these harmonic 4th and 5 are below the band gap of lithium niobate, and that's why we see perturbative scaling. So the number of photons in the fourth harmonic scales as the fourth power of the input photon number. And this behavior is similar for coherent excitation and for bright squeezed vacuum excitation. But the feature that bright squeezed vacuum has uniquely is that look at this region of numbers of photons, or the intensities from 2 to 10 terawatt per square centimeters. Here, the coherent light just damages our sample, but bright squeezed vacuum allows us to see the behavior here, and there are some interesting features which to some extent are reproduced by the FIT, by our theoreticians, but this part is just not accessible for with coherent light. And then we looked at the harmonic 6 and 7, which are above the band gap, and so the behavior is non-perturbative. So for instance, 6 harmonic scales as the third power, and 7th harmonic as the second power for coherent light, rather similar for bright squeezed vacuum. but we see in this range, we see more with bright squeezed vacuum than with coherent light, because the damage threshold apparently for these extreme rare events is higher. And then we looked at not lithium niobate, but silicon, amorphous silicon, for which unfortunately our theoreticians do not have a model. And we see similar things. So bright squeezed vacuum turns out to be less invasive, and the scaling is perturbative for higher photon numbers than in the case of coherent light. And then we see some saturation here. Perhaps this is because of the ground state depletion. That's it. I hope I made it in 45 minutes. So these are my conclusions. I told you about bright squeezed vacuum, that it is a quantum state, non-classical state. The mean photon number can be as high as for a laser source, so 10 to the 13 per pulse, as I showed here in this last part. It has very broad photon number distribution, and it can have mode number tunable. I showed how we can achieve single photon, single mode state. And then I showed you how we apply it to enhance multiphoton effects, how it creates extreme events and drop wave behavior, and how it can generate high harmonic generation in a non-perturbative way. It can be less invasive than coherent light, and also it can eject electrons out of needle tips. And then I must say that all the experiments that I showed are done by people in my group, and I'm most thankful to Andrei Rasputny, who is hopefully in the audience. He did the harmonic experiments, and Alex Mikhailov did the electrons experiments, and we collaborate with Francesco Tani and Peter Homelhoff's group here at our university, the group of Ido Kaminer in Technion, and Denis Seletsky in Polytechnique de Montréal. And with this, I thank you for your attention.
So thank you so much. It was a really nice talk. We have some questions here and comments. So the Kraus, yes, I will let you talk, but your question was regarding the very broad number for photon number distribution of a bright squeezed vacuum, is there a way to make it Poissonian?
Yes.
What?
Okay, go ahead.
Sub-Poissonian.
Sub-Poissonian. Yeah. To make a sub-Poissonian state, we have to turn to the case of twin beams. Let me scroll up on this. In the case of twin beams, where we can take one detector and measure one of the twin beams. Yeah, one more slide. Yeah, so we put one detector here, for instance, and we measure number of these idler photons. And then we just select the pulses where the number of idler photons is below is within some limits. And these limits we can put very narrow. So we can be really request that the number of idler photons, for instance, is between 1 million and 1,000,100. We can do it with our available technique. And then if we only release these pulses, we will also have signal photons having these statistics. So the signal photons will be also within these margins. And such experiments we did. But the question here is how high can be the mean number of photons for which we have this, we can do it. And so far, I think we did it up to 10 to the 5 photons per pulse, but higher we didn't try yet.
Okay, and I was wondering, for the bright squeezed vacuum, it looks like they're squeezing along one quadrature component. Is there then a way to squeeze along the other? Because I would assume this gives you a sub-Poissonian distribution, or not?
No. First of all, wait. Yeah, I'll show you. Right. So I showed here this Wigner function, right? The point is that it rotates in time. It rotates in time with the optical
Yeah.
cyclic frequency. And so when I show this, when I show this diagram, this actually means that we look at the real axis of the real field, or X quadrature, for instance. And sometimes X quadrature is anti-squeezed, so there are such fluctuations. And then half a period, the X quadrature is squeezed. This has nothing to do with sub-Poissonian distribution, because for sub-Poissonian distribution, you have to reduce the uncertainty in the photon number. And you should either act as I described, or it is possible also to take this state, for instance, and displace it so that it's somewhere here, right? So it's horizontally stretched, but the amplitude is non-zero, it's displaced. This is a sub-Poissonian state. This can be done by overlapping a squeezed vacuum, even a normal squeezed vacuum, not bright. Normal squeezed vacuum overlap with a coherent beam on a beam splitter, so that this displaces the state. And depending on the phase of the coherent beam, you can displace it there or there, and depending on this, it will be phase squeezed or amplitude squeezed. Yeah.
And would that bring you to higher numbers of photons per pulse before you set?
Yes, it also brings me to higher number of photons, because if you take this state with G about 1, then, as I said, the mean number of photons is maybe 5, 1, so on, not high, but you can displace it a lot. And then it will be an amplitude squeezed beam or phase squeezed beam. It's also called displaced squeezed light. And the number of photons will be as high as you want by just displacing.
Okay, thank you.
Yeah,
okay, so thank you. Now we move on to other people who would also like to ask questions. There is someone who is anonymous and would like to know how to distinguish the bright squeezed vacuum state from squeezed coherent state in the experiments.
Yeah, in the experiment, you can do homodyne detection. This Wigner function, actually, what I showed here, can be reconstructed in a homodyne tomography experiment. So what you do, you overlap this state on a beam splitter with a coherent state, and the beam splitter should be 50-50. And then at the output, you put 2 detectors and subtract their readings, and then do this experiment for different phases of the of this coherent beam. And this, through inverse Radon transform, will give you the Wigner function. So to distinguish, you just see if the Wigner function sits at the center or it's displaced. Yeah.
Okay, is that fine by you, or would you like to ask further? I cannot unmute you, you are anonymous, but feel free to ask later on. Someone would like also to know about the link between Schrodinger's cat and the topic you discussed.
Yeah. Well, the expression Schrödinger, this is a very correct question, because the state I am describing is just another example of a macroscopic quantum system. But strictly speaking, it is not a Schrödinger cat, because a Schrödinger cat is an entangled state of a macroscopic object with a microscopic object. Here I just showed a macroscopic object that shows quantum behavior. And I tried to outline the limits to it, to which it shows quantum behavior. So I would say 10 to the 5 photons. I find it a macroscopic state. This is true, but it is not entangled with anything microscopic in this case.
Okay. Also, can another anonymous, a lot of people are anonymous today, but it's good that they're asking questions.
Yeah.
Yes, anonymous or not, the important thing is that we have debate.
Yes.
Can we increase the pump intensity to get a bright squeezed vacuum state, whether it will meet the threshold of the crystal?
Yeah, I think it has to do with in principle, that's what we do. We increase the pump intensity, but we do it in the pulsed regime. And if you try to do it in the continuous wave regime of pumping, then the crystal will first burn because what happens here is that at some point the effect starts to depend on the peak power in the pump and not on the mean power of the pump. So as soon as you get some nonlinear dependence on the output of the input, it's better to use pulses. But the heating depends on the mean power of the pump. So it is better to use pulses with not very high mean intensity than just a continuous wave pump with with high mean intensity.
Is it okay? Yes, I hope so. I mean, it's difficult to follow this up, but thank you for your question. Absolutely.
Yeah, it was a very good question.
Now we have Shambhu Kimir. What are the limitations to add another stage, such as to be able to get 100 microjoule? Has this been done?
100 microjoule per pulse. No, it has not been done. I don't think it's impossible, because maybe it's just about the crystal being large enough. You know, in nonlinear optics, you achieve fantastic energies if you don't focus your pump on the crystal. But if you are interested just in the total energy per pulse, it's just about the initial pump energy and the parametric gain. So in principle, we can convert up to 40% of the pump into squeezed vacuum. But to prevent the crystal from burning, I would just use a crystal of this size, and people do it in some fields. Yeah, there are crystals of this size, not the one we use. We use beta barium borate, but there are KDP crystals that are really literally yeah, this size.
I mean, Wilhelm Becker also would like to ask a question. Shambhu, if you would like to follow up.
Yeah, thank you, Maria. That's very nice talk. And I guess, yeah, the peak intensity damage is the issue. And, of course, it would be nice to have large crystals, but there are also limitations. Can you think of like doing in a different stage, like the same thing, but in a different crystal, just adding, another stage?
Other stages.
Yeah.
That's what we do. We use 2 stages amplification. But as I said, we can convert. First of all, the reason why we here do not convert half of the pump to bright squeezed vacuum is because then the statistics is modified. We want to have undepleted pump, and this means that the statistics of bright squeezed vacuum remains the same. Then there are other parasite effects that too bright squeezed vacuum starts to generate other states on its own. For instance, some frequency generation with a pump, or harmonic generation in the same crystal. And again, it spoils the properties. But yeah, we use already different stages.
Okay, thank you. So you have 2 stages, right?
We have 2 crystals. In one, we generate squeezed vacuum. In the other, we amplify it in a phase-sensitive way.
We have a question from Wilhelm Becker. Why is that the effect of a bright squeezed vacuum in the thermal state are so similar, for instance, regarding high harmonic generation? The thermal state is the most classical state I can think of.
Yes, that's again a very good question. And indeed, what we see so far, and what we see is just a broad distribution of the photon numbers that allows to probe the crystal, first of all, easier without changing the mean power, and second, looks like non-invasively, but this is just a consequence of the same the same photon number distribution, not the same, but similar photon number distribution as in bright squeezed vacuum. Here, I think I have a slide where I compare, where I compare the distribution of the photon number in bright squeezed vacuum and in thermal light. And the difference is not that great. It's very tiny. But the important difference is that bright squeezed vacuum consists of pairs of photons, while thermal light doesn't. But this feature is very, very difficult to capture. And we are still fighting on that. We are still trying to invent some experiment where we'll see this this effect. So it's, or in other words, what is interesting to capture and what is hard to capture is whether this variance is for each pulse or from pulse to pulse. You see, we see the field having this value and this value at the same time, or this value and this value at the same time. But the way it can be measured is by looking at pulse-to-pulse behavior. And then we don't know if this behavior happens from pulse to pulse or within each pulse. The difference is between the superposition and the mixture in quantum language. Superposition state is like Schrödinger cat state. It correctly contains quantum superposition. A mixture is like you have 100 cats, some are dead and some are alive. Nothing interesting.
Yeah, Wilhelm, go ahead. You can.
Yeah, okay. You kind of, I typed a follow-up question, and but you kind of answered it already. I was asking if there are effects for the two, the BSV and the thermal state would behave very differently. So I gave the answer already. You're looking.
Well, the answer is yeah. So far, we have some plans, but we haven't made any conclusive experiment yet.
Okay, thank you.
Okay, thank you. I mean, my question, I mean, now asking the end, but I had a similar thought, because if you looked at the picture of the harmonics, they looked so sharp.
Yeah, but that's because of the spectrum of bright squeezed vacuum was much narrower than spectrum of coherent light, but we fixed that problem. Recently, I just do not show the graph. Yeah, you see the spectrum of coherent light was much sharper, much narrower, because coherent pulses, we didn't have coherent pulses with the same duration. Now we do, and the spectra look really the same width, but still there is an advantage in the efficiency. I didn't put this slide here, but it's in the supplementary. I think it's in the supplementary of the paper. I cite this paper.
We have another question. People are on fire today. Thank you, people. Seventh question. It is really good to see this. This is from another anonymous attendee. How does the transition from squeezed vacuum to bright squeezed vacuum affect photon statistics and phase space representation?
Yeah, well, that's what I think I showed. Yeah, so this is squeezed vacuum. Typically, this stretching is maybe 10 times, something like this. For bright squeezed vacuum, if you assume that number of photons is, let's say, 100 or 1,000, the stretching is so much that I cannot draw it. It just it will be just a line. In terms of photon numbers, it's just for squeezed vacuum, when the mean number of photons is about 1 to maybe 5, then you have just discrete numbers here. At 0, some number at 2 photons, some number at 4 photons, and so on, and decaying weights, yeah? With bright squeezed vacuum, you see this distribution stretches up to very high numbers. So the decay is slower. For squeezed vacuum, the decay will be very fast. It will be like very steep. But on the other hand, even very small loss, like a dust particle or like the presence of some absorbent gas, I don't know, at this wavelength, will immediately destroy this odd-even structure, this discrete structure. So there will be almost the same probabilities to have 100 and 101 photons, 100, 1001 photons. It's almost the same. So the odd numbers of photons will appear due to losses. And that's the problem. And that's the same problem as with the cat. Macroscopic quantum states are hard to observe.
Yeah. That is, I mean, that is very interesting. And I'm going to warn people that no cats have been harmed here in this talk.
No cats.
But anyway, are there further questions, comments? Go ahead. I have one question related to the photoelectrons, because you showed that if you have electron emission from squeezed light, that the properties of the light are transmitted to the photoelectrons.
Yeah.
But I was wondering, because if you have a metal tip, you should have focusing, you should have nonlinear effects and all other things going on. Do you account for this?
You mean theoretically? You mean theoretically or in experiment?
Experiments, no?
We don't see much. Well, we don't look at, for instance, harmonic generation. Maybe there is some kind of other wavelengths generated, other frequencies generated. We didn't look at that. We were only detecting electrons. Our setup was not, but maybe indeed these electrons, they accelerate and maybe emit some harmonics. We didn't look into it. At least on my side, I don't know what happens in this respect.
Okay. Now, I mean, even the photoelectrons, they behave then linearly with the field. That's maybe
no. The work function here. So to have the electron released, you have to have your light either energy of one photon to be larger than the work function, or you need many photons. And this is the multiphoton emission. So if you look at this dependence, this is the number of electrons versus the number of photons, mean number of electrons versus the mean energy per pulse. Yeah, it is fourth power dependence. And this means that it's not a single photon photo effect like in the Einstein setting, or what is used in photomultiplier tubes, but it's a multiphoton effect. And it means that we need, actually, from the initial considerations, there should be, I think, 7 photons. If we compare the work function with the energy, with the wavelength. The wavelength is 1600 nanometers here. And the work function is such that you would need 7 photons to jump over the for the electron to jump over the barrier. Yeah, but here it's apparently already non-perturbative regime. So we use the field so strong that it is enough to have 4 photons to eject a single electron, because the power scaling is 4.
Thank you. Ikra Hussain would like to thank you for this amazing talk.
No, thank you. I was hesitating whether it's clear for the audience, but I'm glad that there are so many questions. Thank you very much.
Yes, and we have one more. Yes, so Anonymous, is the bright squeeze vacuum prepared in experiments always phase suppressed, or will it rotate on the phase space?
Yeah, it is rotating in the phase space. As I said, if you have this Wigner function, this is just Okay, well, this picture actually shows the same. When at some time moment the electric field has high variance, high noise, and the next moment it has low noise. This actually means that the electric field we measure is this real part of the electric field, this quadrature. What we measure is this quadrature. What I plotted there is this quadrature. At this time moment, the quadrature has very large uncertainty, but then the figure rotates 90 degrees, and then the X quadrature has small uncertainty. The electric field has small uncertainty. So yeah, this pink ellipse or red ellipse rotates with optical frequency. And every half a cycle, the variance is large. Sorry. Oh, I lost it. The slide. Yeah, half a cycle, the variance is large, and half a cycle it's small again. So it's not phase squeezed; it's squeezed vacuum. A phase squeezed state would be yeah, phase squeezed state would be if we displace this ellipse to the right and put it somewhere here, then it's phase squeezed, because no matter how it rotates, no, I don't have any drawing. I do. Yeah, no matter how it rotates, so first it looks like this, and then with some time it rotates to be here, then it is here, and then it is here, and it is always phase squeezed. So this is what phase squeezed light is.
Very good. Is it fine by you? Just checking. Yes? Well, thank you everyone for joining today, and especially Professor Chekhova. I think it was a very, very, very interesting talk. All of us learned a lot. I'm going to stop the streaming. If you would like to ask questions privately and you don't want to be broadcast all over the internet, just hang in there, because I'm going to finish on YouTube. So for those on YouTube, we had around 10, 11 people joining on YouTube today. For those on YouTube, take good care of yourselves. Have a great weekend, and hope to see you in 2 weeks.